Hello, everybody. Welcome to Chapter 16, Buffers and Titrations. This chapter is a direct follow-up to Chapter 15, which is all about acid and base equilibria. And in this chapter, we're going to apply that to two new concepts. A buffer system is a system that resists a change in pH, and a titration is an analytical technique we can use to find the concentration of like an unknown acid or base. And we have a good amount of math involving both of those mixed with some very important concepts. All right, and the last thing we're going to talk about is indicators, which are chemicals that change their color during reactions, acid and base reactions specifically, to allow us to see when the equivalence point of a reaction is reached. All right, the first thing we need to talk about is the common ion effect. So think about a solution containing a weak acid, hydrofluoric acid. So on our example here, this bottom reaction of hydrofluoric acid, which is not one of our strong acids, it's a weak acid, so it'll dissociate into H plus and F minus ions using this equilibrium arrow, right? So we have this HF making some H plus and F minus, and that's kind of our solution. And we're going to think about this salt, sodium fluoride. This salt, as far as we would know, would fully dissociate into Na plus and F minus. Okay? Well, we have some overlap between our products here. We have what we call a common ion. Both of these reactions produce at least some amount of F minus. So there's two different sources of the same ion, and that's actually going to affect the equilibrium reaction here. Okay, so we'll kind of get into that, but we do not assume in this case, if this is our situation, that our amount of F minus in this example, imagine you're making an ice table for this bottom reaction, and you have this reaction going on at the same time. When you're writing your initial concentrations of acid and proton and anion, you're actually going to have some of this to start. It won't be zero as it normally would. And we're going to look at the effects, such as having an extra ion of the same, an extra common ion from a different source, how that can affect equilibrium. So here are our two reactions. This is called the common ion effect. When a salt is added to a solution containing an ion in common with the acidic solution, in this case, the F minus is the common ion. Okay? So we're kind of looking, this Na plus is pretty irrelevant. Adding more Na plus into this equilibrium reaction won't change anything at all because that Na plus isn't in the reaction. But adding F minus will. It's going to shift the equilibrium a bit. And when you think about shifting equilibrium, you think of Le Chatelier's principle. The idea of Le Chatelier's principle is adding extra F minus ions. I'm increasing the amount of product. It'll cause the reaction to shift to the left. So that just means I'm not going to make as much product as I normally would, right? The main effect that has is it actually lowers your concentration of H plus ions at equilibrium. Okay, one more time. Adding more F minus is actually going to make the equilibrium shift to the left, reducing the amount of H plus. Reducing the amount of H plus an acid produces serves to increase its pH or make it less acidic. It's a worse acid when the common ion is present. Okay? Stated here, the addition of more F minus ions pushes the equilibrium to the left, causing fewer hydronium or H plus ions to be present in the solution. The more concentrated the salt you add to your acid solution here, the more so that equilibrium will be shifted to the left. And we're going to use an example to kind of demonstrate the effect this has. So we want to calculate H plus and pH of HF. If I was asking this question and I stopped here, and I told you its molarity, so I guess I stop here. This is exactly like last chapter. This is a weak acid. I'm going to make an ice table to show how it shifts. The new part of the question is I'm also going to add to the same solution a little bit of NaF, which shares a common ion, F, with hydrofluoric acid reaction. So let's talk about how this is going to react. So I have my ice table here, and we're interested in finding H plus and pH, which means I need to look at my acid and see how much H plus my acid is giving to my solution. So I'm going to write my equation here. HF is my weak acid, and that's in equilibrium, and it produces some hydrogen plus and some F minus. This is exactly how we would write it in our chapter 15 as well. But the thing that's going to be different is our initial concentrations. So my initial concentration of HF is 1.0. And last week we would just go 0, 0. We don't have any products to start. But this time I have my 1 molar NaF also added to the same solution. How we're generally going to think of NaF, or any salt, salts split completely into their ions. At least the ones we use will. Okay? And so if I have 1 molar of this salt, that means I'm going to have 1 molar Na plus ions floating around in solution, and 1 molar F minus ions also floating around in the solution. Now, these NAs, like we said before, are pretty irrelevant. Na plus is not a common ion because it's not anywhere else in this equilibrium. If it was, it would matter, but in this case, I don't really care about that. That's going to float around. It's not going to change your H plus concentration or your pH. But this F minus you have floating around will. So for F minus, you're going to put a 1.0 here on the right, because this is how much F minus is already in your water when you add your acid to it. Now, there's no sources of H plus ions, so that one will still be 0. Functionally, this problem is exactly identical to what we've done before, except we have an extra number here. Now I have to think, which way will this reaction proceed, now that I have a number that's not 0 here? Well, this reaction is still going to proceed to the right. And it has to, because you have 0 of this to start. So when your reaction, for it to go to the left, you have to have some of this and some of this. So your very first step can't be going to the left, because you would have a negative amount of H+. So anywhere there is a 0 at all, your reaction has to shift towards there. Even though there's a 1, we're still shifting to the right. Which means I'm going to lose X amount of HF and gain X amount of these two products. Meaning my equilibrium numbers are 1.0 minus X, X, and 1.0 plus X. So that's the main difference. Instead of just X, you have 1 plus X. And we're going to see how that affects the math. All right, we're given the Ka here. So I'm going to go ahead and set that equal. Ka is 7.2 times 10 to the minus 4th, which equals products over reactants. My first product is X. My second is 1 plus X divided by 1 minus X. And before, we've used our approximation that X is a really small number, which it will be still here. If K is a really small number, X that you're losing is going to be a really small number as well. We've done that before to get rid of this minus X. But we can actually, in this problem, do it to the plus X as well. Adding or subtracting a super small number is pretty much irrelevant. Right? So I'm actually only left with 7.2 times 10 to the minus 4 equals X times 1 divided by 1 is just X. So it actually cuts out any of the math I really have to do here. I just have my answer for X, which is the first question I was looking for. That is your H+. So that's the first of my 2 questions done. I've solved for H+. Now to find pH, I'm just going to use the pH formula. Go to the negative log of my H+ concentration, which is 7.2 times 10 to the minus 4, and plug that into my calculator. Let's get that all set up. Negative log of that, I get like 3.14 as my pH. Right? So my pH is 3.14. Now, if I were to do this exact same problem again, but have 0 here to start, okay, then when I got to this step, this is going to be kind of like a little sidebar. My math would have looked a little bit different. I would have had 7.2 times 10 to the minus 4 equals X squared, X, because this would have been just X instead of 1 plus X. Right? And then I would have to take the square root of this, which would have made this a smaller, or I guess a larger number. 0.072. Take the square root of that. My X would have been 0.0268. And my pH there would have been 1.57. What this number is, this is what my pH would have been if I had none of this to start. It would have been a 1.57 pH. But having this extra common ion, you can see I didn't make as much H plus as I would have otherwise because my equilibrium got shifted to the left. Now this is a little bit confusing wording because my reaction still proceeded right from the initial, but my equilibrium is a little bit more to the left than it would have been otherwise. Right, so I didn't produce as much H plus, and because of that my pH was higher. So having a salt in your solution drastically affects pH, and we're going to be using that idea several different ways today. Okay, and right away, the first way we use this concept is called a buffered solution. So definitionally, a buffered solution is just a solution that resists a change in pH when you add an acid or a base to it. We use this all the time for different chemical reactions. In nature, you see this constantly. Our bodies have a very stringent buffer system to keep our blood at the correct pH. Even a shift of like 0.5 pH in your blood can cause like acidosis and other complications that could kill you. So we have a carbonate system, a buffer in our blood to prevent change in pH. You'll see this all the time for any sort of science you do. If you work in a lab, you use buffer solutions to make sure that whatever you're doing is at the proper pH. Maybe you're trying to grow bacteria or something, right? You need to keep the pH at a very specific level. So a buffer solution is some solution that resists a change in pH upon adding acid or base. So how to make a buffer, the simplest way and the way we're going to talk about is you take a weak acid and its salt, kind of like what we just did in the previous problem. HF was our weak acid, NaF was our salt. We made a buffered solution, which is resistant to changes in pH if I were to add acids to it. Right? So, alternatively, you can make it with a weak base and a salt, functionally the same idea. Notice how your chemicals are only off by one H. Right? This is HF, this is NaF, one H, zero H's. NH3, NH4. You will notice that the NH4 has a Cl attached to it. The NaF has an Na attached to it. And that's just because it is a salt. Salts are far more stable. So when we're making these, we use salt. We can't just add the NH4 plus because the ammonium ion is not very stable by itself. So you can't just get a bottle of it and add it to your solution. But we have these salts. They're shelf stable. We're able to throw them in. And the ion that's not common is irrelevant. It doesn't actually affect anything. Having some extra sodium ions or some extra chlorine ions in your solution will change nothing. Okay, so in your first example of a buffer, the weak acid, HF, will react with any bases that you add, and that'll actually mitigate the change in pH that you would have expected. Adding a base to something should increase the pH, but it'll increase it less than expected because that weak acid and it are going to react and neutralize each other a little bit. Alternatively, if you have a weak base in your solution, it'll react with any strong acid to mitigate a decrease in pH. So having the weak acid and its conjugate, or vice versa, will allow it to accept acids or bases without much change in pH. And we're going to go through some math of calculating the pH of this buffered solution. It's essentially the same math we just did. And then we're going to add some acid and base to it and kind of see how it changes. Okay, so here's our example. We have a buffered solution with some acetic acid. Okay, so when I'm looking at this, this is my weak acid, HA. Right? It's weak because it's not one of our strong ones. It starts with an H and it's given a Ka. And then I have 0.5 molar sodium acetate. Okay, so the common ion I see here is the acetate. Both of them have the C2H3O2. This Na is not really going to be important. So this is kind of like my last example. I have my acid, and I'm adding a little bit of this extra salt, which basically just adds more acetate into my solution. When I write my equation, I'm only going to use my acid, because that's what actually contributes to pH. A common mistake is to accidentally use this chemical to write your reaction with, but you don't. Your salt is going to be added, and that'll affect your initial concentration, but we're not going to write any part of the reaction with it. Okay, so my acetic acid will split. It'll dissociate, it'll lose an H+, and I'm left with its conjugate base, acetate. my initial concentrations of stuff. My acetic acid, it says, is 0.5 molar. I have no source of H+. You'll never have a source of H+ for any of the problems we're going to do, really. So that'll pretty much still always be 0. But my acetate ion, I have 0.5 molar sodium acetate, which means I'll have 0.5 molar of this anion in my solution. Now this is a buffer. I have the weak acid and its conjugate base in my solution at the same time. By definition, we just made a buffer solution. And we're going to try to find the pH of this buffer. Just like last problem, it's going to proceed to the right, so I'll lose 0 over here. I'll lose x over here, I'll gain x over here, and I'll gain x over here. Making this 1.5 minus x, 0.5 plus x. Those are my equilibrium concentrations. I'll go ahead and write my Ka expression. I'll plug in my number 1.8 times 10 to the minus 5. Products over reactants gives me x, 0.5 plus x, divide by 0.5 minus x. Just like last time, I'm going to get rid of the plus and minus x, right? And then 0.5 divided by 0.5, that also cancels, that h equals 1. And just like last time, 1.8 times 10 to the minus 5 equals x. Now, if these numbers happen to be different, I would have to do a little bit of math, but that would be pretty simple. So if these numbers are a little bit different, you can't just cross them out. But in this case, it works out just like that. This tells me how much H+ I have. And then, so if I take the negative log of this, it should be like 4.7 4. That is my answer. Okay. Again, if I were to do the pH of just the acid without this conjugate base, you would expect it to be a good bit lower. Having this conjugate base increases the pH because of the common ion effect. Okay, well, something interesting with buffers is we don't actually have to write out this full ice table to solve it every time. Right? We have a special formula we can use when dealing with buffers to quickly calculate their pH. And here it is. So go ahead and make sure you write that one down in your box. How we read this is the pH of your buffer equals the pKa. Remember, that lowercase p means negative log. So the pKa is just the negative log of your Ka. Then add the log of A minus is your conjugate base. In the previous question, that was our acetate ion. Right, so quickly back, this is your A minus, your conjugate base you have left over. This is your HA. Okay. So all you have to do, you're looking for the concentration of those things, just plug them into this equation. So I'm going to plug in all the information from the previous problem down here. The pH equals negative log is what P stands for. Plug in the Ka from the previous question, 1.8 times 10 to the minus 5. And then plus the log of the conjugate base's concentration was 0.5. Divide by this weak acid also happened to be 0.5. That won't always be the case, but in this case it works. And if you put it on your calculator, it equals the same answer. This equation, and there's one more we use for bases. This is the one for acid. And you know it's for acid because it tells you pH and uses pKa. Okay? This will be a shortcut we use all the time to quickly calculate the pH of a buffer. And to show you how it works, we're going to use it 3 times here to calculate the pHs of each of these 3 solutions. Okay, so I want to calculate the pHs of these. I'm just going to kind of have my equation here. pH equals pKa plus the log of the conjugate base's concentration divided by HA's concentration. So when we're identifying these, your acid is the thing that has the H, just like this has the H. So here's my acetic acid. This would be the concentration of my A minus. So when I'm plugging this in, pH equals pKa is the negative log of the Ka, 1.8 times 10 to the minus 5. This number has to be given to you. I'm just using the same one from the previous problems. plus the log of, and you can put this whole thing in parentheses like this, and then just take the log of the answer. My A minus concentration is 0.5, and then my HC2H3O2, my acetic acid, is 0.25. If I solve this in my calculator, that'll give me the answer. When I plug this first part in, I get 4.74. Plus, this is the log of 0.5 divided by 0.25. So I can type that whole thing into my calculator. All right. But if you're not sure, you could just do 0.5 divided by 0.25. That just equals 2. Take the log of 2, and that's my answer there. 0.301 is that second term. Now I'm just going to add these two together. And my final answer is 5.04. That's it. You don't have to draw the whole ice table. You're totally welcome to. You'll get the exact same answer, but the Henderson-Hausbach equation saves you a lot of trouble. Okay, I didn't get the same answer as last time because this time I didn't have the same amount of acid and base. If you have the exact same amount of acid and base, the log of your numbers is the same, and the log of 1 is just 0. So when you have the same amount of acid and conjugate base, this whole term goes away. It just turns into plus 0. And here, that was our answer. So when you have the same amount of acid and base, your pH actually equals your pKa, because you can ignore all of this term. The third example will show us that. So in this first case, again, I had more of the conjugate base, and look, it caused my pH to go up. Having extra of the conjugate base will increase your pH. In the second example, I have more of the conjugate acid, so I'd expect my pH to be slightly below 4.74. And to do the work to show that, I have the pH is the negative log of that same number, plus the log of acid over base. My acid is 0.5, my base is 0.75. I know my first term equals 4.74, it's the same as last time, but this time when I add, I'm going to do 0.5 divided by 0.75 equals that. Take the log of it, and I get a negative number this time. 4.74 plus negative 1.76 equals 4.56. So as expected, my pH went down a little bit because I have a little bit more acid and a little bit less base. So that adds up in my head. Now, the last example we kind of spoiled already, but of the negative log of my Ka, we're still using acetic acid, plus the log of base over acid, 0.005 divided by 0.005. The log of this just as 1 is 0. So anytime you have the exact same numbers, that just goes away, and your pH is just 4.74. And that's it. Those are your three answers. So calculating the pH of a buffer, the easiest way is using that Henderson-Hausbach equation. You're totally welcome to use a full ice table. You'll get the exact same answer. All right, so when the point of the buffer is to be able to add some acid or base into it. So when we add an acid or base to a buffer, there's a stoichiometry calculation we have to do. We have to understand how much of our buffer is neutralized. Okay? So if I add an acid to my buffer, it is going to react and take away some of the base. The base is the conjugate base, the A minus. So adding an acid will get rid of some of the A minus and actually produce more of the weak acid, and I'll show you how that works. And the opposite's true. If I add a base to my buffer solution, it's going to react with the HA, with the weak acid. And when that happens, it'll reduce the amount of weak acid and make a little bit more of my conjugate base. But the point is, it doesn't change the pH very much at all. You can calculate the new starting amounts of acid and base, and then do an equilibrium calculation based on your new concentrations. So, to spoil, this sucks. This math is pretty hard. There's a lot going on. You have to do stoichiometry and ice tables all at the same time. To be fair, we don't have to do this full calculation on the AP exam. You won't have to calculate the exact change that occurs. But I'm going to do this one example with you. You won't have to do it on your worksheets or anything necessarily. But you have to understand a lot of the concepts that go on. And seeing a full example, I think, is really helpful. And we can actually show how little the pH changes. So we're going to calculate the change in pH that occurs when I add some NaOH, which is my strong base, to 1 liter of the buffered solution we just used. So if we kind of remember, in our last example, the pH of our buffer was 4.74. Exactly, was the first example that we did. So with my pH of 4.74, I want to see what adding some base will do to this. Now, adding a base to this should make the pH go up. And if I was just taking this base and adding it to water, the pH would go up tremendously. But because I'm adding this to a buffer, the pH won't go up as much as I was expecting. So, just like when we look at salts, I'm adding NaOH. The OH is, again, the only thing I care about. Adding extra sodium doesn't do anything. But you can't just have OH in a bottle. It has to be attached to something. So that's why I have some NaOH for adding. So I'm going to simplify it by starting my first reaction by just writing OH. Realistically, you'd get the same thing with Na, but it's just a spectator ion. It doesn't actually participate. Because of that, I'm just going to write OH. So I'm starting with OH, and I'm going to add that to my buffer. And I'm going to try to figure out what it's going to react with. Okay? Well, base reacts with acid. So my first reaction here, this isn't an ice table. Notice, this is an ice table down here, but we're not there yet. This is actually lovingly known as a bra table. Before the reaction, during the reaction, after. And we're using this just to calculate how much of my buffer changes. So I'm adding some base. It's going to react with my acid. So here, I'm going to put acetic acid. This is my first reaction that's going on. My base and my acid are going to react. And this isn't an equilibrium. It's just a regular right-facing arrow. Now, this OH is going to take the H away from the acetic acid to make H2O. We don't care about the H2O because it's a liquid, so I'm going to put it on the outside here. The important product is the conjugate base, C2H3O2 minus. As usual, H2O is irrelevant. So this is the important reaction going on. I'm adding base. I put the acid on the left because acids and bases are what neutralize each other. When these react, they produce water, which is irrelevant, and some C2H3O2 minus. Before my reaction starts, so basically in my problem, I'm going to show how much of everything I had. So my acetic acid was 0.5. My acetate ion was also 0.5. And my OH minus, I had 0.01 moles in 1 liter. So it's also 0.01 molar. So if I have my molarity of everything, here are my numbers. So I'm adding some some base to this reaction. These two things are going to react with each other as much as they can, and they'll react until all of my OH minus is consumed. Once all of that is used, my reaction stops because my limiting reactant is gone. So I'm going to lose 0.01 of this, 0.01 of this, but I'm going to gain 0.01 of my product. Like I said, these will react fully until all of my OH minus is consumed. At the end of my reaction, all of my strong base is gone. So it's not contributing in any way to the pH now. Some of my acid got consumed. I'm only left with 0.49 molar. And my conjugate base, I made a little bit extra of it. It's now 0.51 molar. So all that's happened so far, I haven't done any sort of ice table yet or Henderson-Hasselbalch equation. This is just kind of showing what happens when I take my base and I add it to my weak acid. The base gets fully used up because it ran out. It used up a little bit of my acid and made a little bit extra base. All that's going to change down here. This is my equilibrium, my ice table. So here I'm going to have my acid. It's going to react as it did before to make H plus and C2H3O2 minus. So we're solving the same problem like we did before. The only thing different is this first step changed these numbers a little bit. And we had to do that change before we can get to the ice table. So literally the only thing different is I have 0.49 of this instead of 0.5 and 0.51 of this instead of 0.5. Still have 0 H plus in my solution. All right, I'm going to go ahead and solve this. Minus x plus x plus x, 0.49 minus x, x, 0.51 plus x. Set up my Ka, 1.8 times 10 to the minus 5 equals x times 0.51 plus x, divide by 0.49 minus x. Get rid of my plus and minus x because I don't care about them. Now I'm going to solve for x. I have to do a little bit of math. I'm going to multiply by 0.49, then divide by 0.51. Right, so times 0.49, divide by 0.51. I get a very similar answer to what I started with, but it changed a little bit. X is 1.73 times 10 to the minus 5. That's how much H plus I have. To find the pH of my solution, I just take the negative log of that answer. Oops, I did the wrong thing. 0.0000173. My pH is 4.76. Remember, 4.74 is what we started with. We added base, and the pH marginally changed. It hardly changed at all from adding this base. That's the point of a buffer. All right. Alternatively, you didn't have to do the second part. That ice table was unnecessary because you could have just done another Henderson-Hasselbalch equation. So here's the work for that if you'd like that as well. Oops. The pH is pK plus the log of the acid, the base over the acid. Plug in the same numbers we used, and then you can find your pH this way also. So the Henderson-Hasselbalch replaces the weak acid equilibrium step, the ice table. Okay, and we're just going to quickly compare that to the change that would happen if I just added this to pure water. So my problem here, we're going to start with pure water. We're going to assume it's normal temperature and everything. So my pure water has a pH of 7. And I'm going to add 0.010 moles of NaOH. So that means I have 0.01 molar NaOH. Right? It's just moles divided by liters, so I just did 0.01 divided by 1 equals molarity. Oops, what's up there? 0.01 moles divided by 1 liter gives you molarity. Well, if I want to find the pH of this, I can't do it immediately, but I can find that pOH is the negative log of this. The negative log of pOH, 0.01 is 2. Which means the pH, you just do 14 minus 2, is 12. So my pH went from 7 to 12 when I added this to pure water. It changed 5 times. And each level of pH, remember, is a 10 times change. So my solution got 10 to the 5th times more basic from adding it. In the previous example with a buffer solution, I only got marginally more basic. That's the purpose of a buffer, to resist this change in pH. Okay. Now we're going to do a couple more examples here. This, I want to calculate the pH of a buffered solution containing 0.25 molar NH3. This time, NH3, the only difference here really is, NH3 is a base, which it's one you should recognize. It's ammonia. But if you aren't sure what it is, look at what Ka gives you. It gives you a Kb, B for base. So this time I'm going to have my NH3 and its salt, NH4Cl. So this is an opposite. This is a weak base buffer. This is a weak base and its conjugate acid. So it's going to be the same thing. It's just a little bit backwards, mainly just when we write our reaction. All right. So my reaction this time, what I'm going to start with is the thing I have the KB for, right? So whichever it gives you the K for, that's what your initial thing is going to be. That is the thing that is splitting apart and dissociating. So I have NH3. This is a base, so it's not going to lose an H. It's going to gain a base, gain an H instead. So it makes NH4 plus. The second product is OH minus. And if you're like, where'd the O and the extra H's come from? Technically, when this reacts, it's also reacting with an H2O molecule, which is providing the other H and providing the OH here. You can show this optionally if you want, but everyone knows what you mean if you just include what's here. Right? So my initial amount of NH3 is 0.25. My initial amount of NH4, I have a little bit of that as well, 0.40. Again, the Cl doesn't matter, it's a spectator ion. Only the common ion, NH4 plus, matters. And I start with none of my hydroxide. My reaction has to go to the right because I have a 0 over here. Minus x, plus x, plus x. 0.25 minus x, 0.4 plus x, x. We're going to do the exact same thing we were doing before. Kb is 1.8 times 10 to the minus 5. You'll see this number all the time. Is 0.4 plus x times x divided by 0.25 minus x. Get rid of plus and minus x because they're irrelevant. Solve for x. So I'm going to do 0.25 times 1.8 times 10 to the minus 5, then divide by the 0.4 to get my x by itself. 8, I get 1.13 times 10 to the minus 5 equals x. Remember, this time x tells you how much OH minus you have, right? X here tells you OH minus. So I can't find the pH right away. I have to find the POH, which is 4.95. So to find the pH, I just subtract 14 from that. So 14 minus 4.95 is like 9.05. It's your final answer. It's very common to forget this last step when you're doing bases. So just don't forget bases need a pH above 7. Okay. Just like with acids, we have a Henderson-Hasselbalch equation we can use for bases. Now it's just a little bit different. You solve for POH and use pKb instead of pKa. But the thing that is most commonly missed is actually this last part. The log this time, your conjugate acid is what's on top, and your conjugate base is what's on bottom. Your weak base is what's on bottom. So if you think about it in terms of acids and bases, it can get confusing because they're flip-flopped between the two reactions. But the easiest way to think about it is it's always products over reactants, right? If you look back at our work from the last problem, we're just taking these numbers, 0.4, 0.25, and plugging them into the Henderson-Hasselbalch equation. They'll be in the same order. The order is always products over reactants. So I like to think about it the same way. When I'm using the Henderson-Hasselbalch equation, start with how much product you have on top, divide by reactant. And that'll work either way. You end up with the same answer. Looks like there's a slight rounding difference, but no biggie. 9.06. So to summarize buffers, buffered solutions contain relatively large concentrations of a weak acid and corresponding weak base. They can involve a weak acid, HA, and a conjugate base A-, or a weak base B and its conjugate base BH+. When H+ is added to a buffered solution, it reacts with the weak base. If OH- is added, it reacts with the weak acid. When OH- is added, it reacts to completion with the weak acid present. The pH in the buffered solution is determined by the ratio of the concentrations of weak acid and weak base. As long as the ratio remains constant, the pH remains constant. This will be the case as long as the concentrations of the buffering materials are large compared to the amount of acid or base added. Okay, so to break down what's important here, You are not responsible for the entirety of that math. Specifically, the section where you add an acid or base to your buffer to calculate the exact change in pH is no longer assessed on the AP exam. Right? You will not need to calculate how pH changes when you add an acid or base to your buffer. But lots of things you do need to know from that. You do need to know that if you add an acid to your buffer, it'll lower the pH, but only by a little bit, because a buffer resists that change in pH. You'll need to know that adding a base to your buffer will raise its pH, but only by a little bit because the buffer resists a change in pH. And you will need to know how to calculate the pH of a buffer before anything is added to it. So you still need to know how to use those Henderson-Hasselbalch equations. You just don't need to also add more acid or base on top of it before you do the math. The next thing about buffers is buffer capacity. Basically, capacity is how much stuff you can hold. Buffer capacity is basically how much acid or base you can accept before the buffer is no longer good. The amount of protons or hydroxide ions a buffer can absorb before its pH changes significantly. Generally, significant change is a pH change of 1. If your pH changes by 1, it goes from a buffer of 4.5, it goes up to 5.5, that means your buffer is kind of dead now. It's kind of busted. So, the main thing that determines your buffer capacity is just how much weak acid and conjugate base you use. The more of it you have, the more resistant to change your buffer is, and the more capacity it has. A buffer with large capacity contains a large concentration of the buffering components. All right, to choose a buffer, there's a couple of criteria we're going to look at. So, large changes in this ratio is what changes the pH. It's not good. The optimal buffering conditions is when you have HA and A- are exactly the same. Okay? So what you want to do is when you're choosing chemicals that you want to use to make a buffer, you want the pKa's of those chemicals, of the acid, for example, to be as close as possible to the pH of the buffer you're trying to make. So if you want a buffer with a pH of 4, you need to find an acid whose pKa is around 4. pKa is just a way to measure the acid strength. So you want it to be as close to 4 as possible. So if you're given a choice, different chemicals have different pKa ranges. You want the pH and pKa to be really close to each other. So here's an example of some things you can do with buffers. All right. So you are tasked with creating 0.5 liters of a buffer using the minimum amount of stuff. So our goals for this, we want our pH to be 4.3. Okay. All right. When you add some sodium hydroxide, the pH doesn't change by very much. It doesn't change by more than 0.5. And we can choose from the following acids to make our buffer with. So, number 1, I'm going to choose my buffer system and justify my answer. So, let's actually go here. So when I'm looking at my buffer, its pH wants to be 4.3. So all I have to look for is which of these acids have the pH that's closest to 4.3. So it's definitely not the last or first one. 9.2 and 3.2 are the furthest away. It's between these two middle ones. These would both probably be reasonable buffers, but hydrozidic acid, HN3, looks like it's the best choice. Its pKa is relatively close to the pH I'm looking for. 4.72 is the closest of these numbers. It's only 0.42 away. So when I'm answering that, that's what I'm going to say. I'm going to choose HN3 because its pKa is closest to the desired pH of 4.3. And that's it. When you're looking for which thing to use, that is your system you're going to use. Okay? So, HN3 is an acid. It looks like NH3, but it's backwards, so don't get it confused, right? When this reacts, it's basically going to turn into, oops, I even wrote it backwards. HN3, when it reacts, this is an acid, so it's going to lose its proton and make its conjugate base N3-. So those are the things we're looking at. HN3, this will be our acid, HA. N3- will be our A-. All right, and I want to determine exactly the ratio of these things I need to each other to create my pH of 4.3. All right, so I'm going to use the Henderson-Hasselbalch equation to figure this out. Okay, so I'm going to start by plugging in the pH and pKa that I have. So I want a pH of 4.3. The pKa of this acid is 4.72. And then plus, I'm going to leave the log of this whole thing as it is. All right, I'm going to simplify my terms. I'm going to subtract 4.72 over here to get my answer. So I'm going to do 4.3 minus 4.72, and I end up, I'm going to write it here, 0.42 equals the log of A minus over HA. And what I need to find is basically what ratio of this, when I take the log, equals 0.42. So I need to solve for this whole term. To get rid of the log, I do the inverse, which is 10 to the power of it. So I have 10 to the power of negative 4.2 equals 10 in log cancel, and just give me the unit I'm looking for, which is just this ratio. So I'm just going to plug in 10 to the power of negative 0.42, and I get 0.380 as my answer. So this is the ratio. So I need more HA and less of this. This is basically like saying for every 38 A's, I need 100 HAs. Right? So that's what the ratio is saying. It doesn't tell you exactly how much of each thing, but if you're able to figure out one, you should be able to figure out the other. So this is my ratio, which makes sense. My pKa is 4.72, which I need to lower it. I need to make it more acidic. So I use a little bit more acid than I do base. And this is the exact calculation for how much. Next, write the reaction of OH minus reacting with my buffer. OH is a base. It's going to react with the acid component, HN3. It's going to react with some OH. It'll react to completion because this is a strong base. The H and the OH will make H2O. And then the remaining is just this N3 minus. That's your reaction. Acids and bases together make water and a conjugate base. And 4, will the pH of your solution increase or decrease as you add NaOH? Adding a base makes it less acidic, so the pH increases. It shouldn't increase by a lot, but it should increase a little bit. All right. That is buffers for the most part. And our next goal is titrations, which we should be a little bit familiar with, but there's a couple different types of titrations we have to look at and a couple of key points we need to mention about them. So, a titration is used to determine the concentration of an acid or base in solution. Hypothetically, if you have an acid and you don't know exactly how strong it is, titration is an analytical tool you can use to figure it out. So it's a process in which a solution that you know its concentration, called a titrant, is dispensed a little bit at a time into your acid until they're completely neutralized. The neutralization point is called the equivalence point. The equivalence point is when you have the exact same amount of acid and base, and then we can do some math to figure out, do some backwards math, kind of to figure out how strong our acid would have been when we started. Generally, we'll use indicators to kind of help us figure out where a reaction's going. Phenolphthalein or methyl red are two examples. They're added to the analytes, to the unknown thing, to kind of help you figure out when the equivalence point has been reached. These are chemicals that change color as pH changes. So, for example, phenolphthalein is a colorless solution when in an acid, but if the pH is raised to about 8 or so, it turns bright pink. So your goal is to keep titrating until you get just to that first little faintest amount of pink, and that is your equivalence point. That's when your moles of acid and base are equal, and then you can do all sorts of math, whatever you want, to figure out how strong your acid or base is. Alternatively, the progress of a titration is more accurate if you monitor the pH as you go with like a pH probe, but sometimes that's not available. So we have a couple of problems. And if you're looking at your notes, you're probably like super freaking out looking at all these tables and stuff like this. This is a super extra example. Basically, we're doing several different problems together. Just to kind of show you all the different possible scenarios a titration can give you. And it is important to know all the different scenarios. The main idea of these problems will be that depending on how much acid and base you have, you actually end up with different scenarios. And we need to kind of know what to do with all those scenarios. So 50 milliliters of my acid, and I know my acid strength is titrated with 0.1 molar NaOH. I want to calculate the pH of my acid initially after 20, 100, and 150 milliliters of my base have been added. So basically, I want to check what my pH should be at each of these steps. So I have 4 different problems I'm looking to solve here. I want to know the initial pH of my acid, which should be easy to find. I want to find the pH after I add 20 milliliters of this base to it. So in my head, I'm thinking I'm adding a little bit of base to my acid, so the pH should be a little bit higher. Okay, and then I'm going to check after 100 milliliters of the base have been added. Okay, so the pH should be even a little bit higher. And then once 150 milliliters of it have been added. Okay, we're going to do this problem a couple of times and just kind of show you how you do this. Now, I already said that already, but a key idea here is what type of acid and base are you using? It depends. It will change your math a lot if you're using strong acids or weak acids and bases. Now, in this case, it's a simpler example. HNO3 is a strong acid. NaOH is a strong base. So that's going to simplify things a little bit for us. So, let me jump the gun on next page. Okay, before I add any NaOH to this at all, what I have is 0.2 molar nitric acid. And I want to find its pH. Right, that's what I'm looking for, so pH at each of these steps. This is a strong acid, so it's going to be pretty easy. All of this turns into H+. So when I find my pH, I just do the negative log of 0.2. And that is decimal 0.699. That's your first answer. Very common mistake is when forgetting that strong acids are a lot simpler and you don't have to set up the ice table or do anything fancy like that. You just all of your acid turns into H+, use the pH formula. So I'm starting with a pH of 0.699. And here I'm going to add a little bit of acid to it. Right? Sorry, I'm adding base to it. I'm adding a little bit of base. My reaction will be my acid I started with, HNO3, plus my base, NaOH, making, all right, so here I have the H and the OH will bond together to make H2O. Your NO3 minus will be left over as this loses its H. And if you really care, you have an Na plus floating around. Alternatively, right, Na never will matter in this case. So you don't have to include it on the left because it's just a spectator ion. You don't have to include it on the right. You're welcome to. It doesn't change anything. The important thing is you're adding OH. Na is just kind of your carrier. It spectates. It doesn't actually participate. So either way you write it, this is your reaction you're looking at. Adding some OH minus will join with the H to make H2O. NO3 is your conjugate base. All right, so the things that really matter here are my products. My reactants won't matter yet. Maybe eventually they will, but for a strong acid, strong base, they won't at all. So before my reaction, I need to put everything in moles in this table. And the reason why is because I'm actually changing the volume. As you change the volume, this is getting watered down. So to avoid that messing up our calculations, this will probably be necessary in most, if not all, titration problems like this. You're going to put moles of everything you have into your calculations. So my HNO3 I'm starting with is 50 milliliters of 0.2 molar. So 0.2 is moles divided by liters, 0.05. Multiply that and you get 0.01 mole to start. So my HNO3, I have 0.01 moles. I've added 20 milliliters of my base, so 0.1 molar is moles over my volume, 0.02, multiply all that, 0.002 moles of base. Right, so this is my OH minus, this is my HNO3. So in this case, this is essentially what's happening. I have 0.01 moles of HNO3 in my beaker, and I'm adding 0.002 moles of OH minus. And these two guys are going to react as much as they can and make these products until they are all gone. This is my limiting reactance, so this is how much is going to be lost. I'll be left with none of this after the reaction. And I'm going to lose 0.002 of this as well. And I'll be left with 0.008 moles of acid remaining. So this is kind of what's happening in my first step. I add a little bit of acid, which neutralizes, add a little bit of base, neutralizes some of my acid. I'm only left with a little bit less acid than I started with. But I want to find its pH. pH is the negative log of my H plus concentration. Now, this is my H moles, but I actually need this to be in concentration to be able to solve for pH. So I'm just going to do a third version of moles divided by liters. I have to think about how many liters I have now. I started with 50 milliliters, but I just added 20 more. So my actual new volume is 0.07. Because we're adding volumes together, that's why we have to go through these extra steps of turning things into moles, because it will change this number. If I just used 0.008, then I'm not taking into account that I've added a little bit more liquid and diluted this down a bit. And my new concentration is 0.114. So I've started with 0.2 molar, and now I'm down to 0.114 molar. That's what I'm going to plug into the pH formula. And my new pH is 0.942. Okay, that's a lot here. Maybe I should have labeled all these steps. HNO3, this is my OH minus calculation. This is my after HNO3 calculation. Should have done a better job like keeping all that organized. I will in the next one. My pH has gone up a little bit because I've added some base to it. All right, so I have the same thing going on in the next equation. My reaction is still the same. I still have HNO3, OH minus reacting to make the products I don't really care about. Okay, so before my reaction, we're kind of restarting. So we're going back to having 0.01 moles of this, right? And now I've added 100 milliliters of 0.1 molar NaOH. So my NaOH, its molarity is 0.1 moles per liter, 0.1 liters. I have 0.01 moles of NaOH this time. Okay, which means you actually have the same amount of both of these, which means all of it is going to be used up. You'll have 0 moles of acid, 0 moles of base. Your pH is 7. You have no acid or base. You have a completely neutral solution. None of your products here are acids or bases, right? So they're not going to affect the pH at all. That's a little bit misleading, but go with it. H2O is technically an acid or base, but it's neutral. And then NO3, because it's the conjugate base of a strong acid, is a really, really, really weak base. It's so weak, in fact, that 0% of this will react to turn back into HNO3. Basically, when you have strong acid and strong base, their products don't affect the pH at all. So the pH is 7. And if we were showing this on like a titration curve, you would see that this is the exact point in the middle. It's the exact equivalence point. And if I was looking at my scale, it should be exactly at 7. That's not true for a weak acid or weak base, but when you have strong acid, strong base, it simplifies it like that. Now I do have one more to work out here. This time I've added even more NaOH. So I have the same reaction, HNO3, OH minus, makes my products. All right, I have 0.01 moles of this still, This time, my NaOH concentration, I have 0.1 molar still, equals moles per liter at 0.15 liters this time. So I have 0.015 moles. Which means in this case, I have more base than I do acid. This will be my limiting reactant, so all of this will be used. I'm left with no acid, but I do have a little bit of base left over. So this will contribute to pH, so I do need to calculate that. I have 0.005 moles of OH minus over my new volume is 150 plus the original 50 I had of HCl. So I now have 0.2 liters or 200 milliliters. Right, going to do my math. 0.005 divided by 0.2 is 0.025 molar OH minus. I can find the POH from that by taking the negative log. My POH is 1.60, meaning my pH, I do 14 minus that, and you get 12.4 as your answer. Okay. So we can kind of check the pH at any point during the titration process. Essentially, you're doing a stoichiometry calculation, a limiting reactant, how much of one of your reactants is left over. You can use that to find the molarity of your leftover acid or base. Use that to find your pH or POH. Right? So, plotting the pH of the solution being analyzed as a function of the amount of titrant added. So here's what a typical graph will look like. And for strong acids, strong bases, it should be nice and symmetric like this. You'll notice the pH goes up very, very slowly and then jumps up really, really fast as you get close to this equivalence point. The exact center of this sort of curve, right, the exact middle of our transition area here is called the equivalence point. And as we said before, if exactly right, the pH should be exactly 7 at the equivalence point for a strong acid and strong base. Okay? The equivalence point is the point in titration when enough titrant has been added to react exactly with the substance in the solution being titrated. The moles of acid and base are exactly equal, like the third part of the question we just did. The titration curve of a strong acid with a strong base will have this nice symmetric shape. That's what you're looking for. The pH at the equivalence point will always be 7, but unfortunately you can also use weak acids and weak bases, which complicates things and adds a couple extra steps. So for weak acid and strong base, or vice versa, if one of your things is weak and the other is strong, that's the other example we need to be responsible for. Weak acid and weak base, if you use both weak things, it gets really messy, and those aren't anything we have to worry about. But a weak acid with a strong base or a strong acid with a weak base, those are problems we should be able to handle. It's essentially the exact same setup we were doing, right? The difference is that if you have a weak acid remaining or a weak base remaining, when you go to find its pH, you have to do an ice table and do all of that nonsense. Because it's a weak acid or a weak base, you have to do that extra step to calculate pH. So you're going to do essentially step 1 is exactly what we just did in the previous problems. You do a stoichiometry problem to figure out how much H plus or OH minus is left over, and then find the pH, or then use that to basically find how much of everything you have. But the second step is you have to do an equilibrium problem if you have weak acid left over. So I'll show you what that looks like. So we have the same problem here. This is essentially the exact same problem, except if we look at our titrations, we now have a weak, a weak acid. Everything else is exactly the same. I'm adding a little bit of base to it, a little bit at the time. I'm going to calculate the pH at each of those steps initially and as I start to add base. So I just need to be a little extra careful when I calculate the pH at each of these steps. All right. So let's show you what this one looks like. All right, so here is my equation. I want to know my initial pH before I add any NOH. So all I have at this point is I'm just right here. Some acetic acid. That's all I have. That's an equilibrium reaction because it's a weak acid. it makes hydronium, and it makes acetate. My concentration of this is, from the problem, just 0.1. And I don't have any of this other stuff to start. I lose x of this, gain x of these things. I get 0.1 minus x, and x as my equilibrium concentrations. So this is a straight out of chapter 15 problem here. My Ka is 1.8 times 10 to the minus 5 equals x over 0.1 minus x. I can get rid of the minus x term, but I can't get rid of these multiply x's. Multiplying by a small number does change things. Subtracting a small number doesn't. All right, I'm going to solve for x. I'm going to multiply 0.1 up here, and then take the square root to get my term for x. Times 0.1, square root it. X this time is 0.00134. X happens to tell me my H plus concentration as well. So I take the negative log of this to get my pH. My pH is 2.87. This is essentially the only difference, is after I do my math, I have to do an ice table as well to find my new pH. I can't just skip to this step like you can for a strong acid. All right, let's see how the other steps go. I'm adding a little bit of my base to my acid. So to write my reaction, I'm going to have my acetic acid, I'll just write it here, plus my base, we're just going to use OH minus to make it simpler. This is going to be a full right arrow because I'm adding acid to a strong base. These things are going to react with each other and neutralize. Their two products will be my acetate anion and a little bit of H2O. I drew the H2O outside the box because, as usual, no one cares about H2O. But these are the other products. All right, I'm going to write before my reaction how much of everything I had. Right, again, I'm going to need to use moles because I'm adding extra volume. It's going to change all my molarities when I do that. So I'm going to go ahead and calculate all my moles of everything. So my acetic acid here, if I go up here, 50 milliliters of 0.1 molar. So try to keep it better organized. All right, I'm going to have 0.1 molar equals moles divided by 0.05. I have 0.005 moles of my acid before anything happens. Okay, my NaOH up here. So I'm going to do this one right here. 0.1 is moles divided by 0.025. Multiply that together, and I get 0.0025 moles of my OH minus. And I have none of this. I don't have any common ion things going on, so I start with 0 of this. All right, so these two things are going to react together. My acid and my base are going to react fully. This is my lower number, so that's how much it will react. It'll react until all of it's gone. And then after, all of my OH minus is gone, and half of my acetic acid is gone. The main difference between a weak acid and a strong acid is your product matters. This is your conjugate base. It's really important. I also have to include how much of that is made. It's a 1-to-1 ratio, so if I lose 0.0025 of this, I make 0.0025 of this, and I end up with that much of my product. Now this matters because now I have a buffer. Doing a weak acid strong base titration, or vice versa, makes a buffer solution, which is going to affect some things. So, first thing I did was all my math calculations here. The goal was to find how much acid I have left, how much base I have left, if any. This is 0. So in this case, this isn't going to affect my pH. I don't have any left. And this part also matters as well. So now I'm going to make an ice table using all of these numbers, using my amount of acid and my amount of base to find my pH. Oops. Actually, we'll just do it here. Because I could do this all with ice table, but instead I'm just going to use the Henderson-Hasselbalch equation. Gotta practice that anyways. Oops, plus the log A minus over HA. Sorry that's so sloppy. All right, I want to find my pH, my pKa. My Ka was given to me in the problem, so I'm just going to do the negative log of 1.8 times 10 to the minus 5 plus the log of my acid, or my base, my A minus, 0.0025 over my acid, 0.0025. Hey, those are equal. That whole thing goes away. So my answer is just the pH of this, which is 4.74. So that's the main difference, is when you're doing a weak acid and strong base, after you get your numbers, you have to use the Henderson-Hasselbalch equation to find your pH, not the normal pH formula, because you have a buffer. And something interesting happens here. So this is a special term called the 1/2 equivalence point. Okay, if we kind of look at our math here, exactly half of my acid has reacted and turned into base. And there's a special rule at the half equivalence point, because this whole term goes away, this all disappears. And what you're left with, pH equals pKa. And this is true for any half equivalence point. The pH of the solution at that time is the pKa of your acid. And this is actually how we find the pKa's of acid. We titrate them exactly half to the equivalence point and use that to find their pKa's. It's just whatever the pH is at that point. Okay, we are not done yet though. We have a couple more parts to do. 50 milliliters of NaOH has been added. So I'm going to have the same reaction, HC2O2, OH minus, makes our conjugate base, which is important, and water, which is not. I'm going to go back to having the same amount here, which is still 0.005 moles, right? And we're restarting, so we're starting with like none of this still, right? And OH minus this time, this is how much I have. At 0.1 molar, mole over 0.05 liters, means I have exactly 0.005 moles of OH minus. Okay, so here is going to be the equivalence point. I have the same amount of acid and base, so all of this is going to be used up. 0, 0. So both of these are gone. They don't affect the pH at all. But I am left with some of this. I have some of my acetic acid left over. And this does contribute to the pH. All right. So what I have here is I have just a little bit of base left over. Now, we can calculate the exact pH of this, but because I have 0 of this, I can't use the Henderson-Hasselbalch equation this time, right? Because I'll have to divide by 0, which will give me an invalid answer. So I can't use the Henderson-Hasselbalch, but wouldn't make sense because I don't have a buffer anyways, because I don't have any of the acid left. All I have is the base. So in this case, I have to go to an ice table. So you can only use the Henderson-Hasselbalch when you have both of these things. My reaction, though, I'm not going to put my HC2H3O2 because there's none of it left. The only thing I'm looking at that contributes to pH is my acetic acid. So my C2H3O2 minus is going to react. And this is a base, so when it's added to water, which we don't really care about, it's going to take an H to make the acetate or the acetic acid, and some OH minus. So this is our reaction. The H2O I'm going to put over these shaded in ones because they don't matter, but all the other stuff will. Okay, so again, we're doing this because all I have left over is this, which does affect the pH a little bit. So I just need to use this to calculate the pH. So my amount of this is 0.005, just copying that from up here. None of this in my solution, they're both 0, minus x plus x plus x, 0.005 minus x, X, and X are all my numbers here. I'm not going to use a Ka, I'm going to use a Kb because I'm looking at the bases dissociation. But I don't know the Kb of acetate. All I was given was the Ka, which is acetic acids, which is 1.8 times 10 to the minus 5. But I need the Kb because I'm using a base here. It's gaining an H+. We have another relationship we can use to find that. Ka times Kb is always 1 times 10 to the minus 14th for a conjugate acid-base pair. So if I plug in acetic acid's Ka, I can solve for the Kb using this formula. So I have 1.8 times 10 to the minus 5 times Kb equals 1 times 10 to the minus 14th. Divide both sides by 1.8 times 10 to the minus 5. Divide by 1.8. And you get 5.56 times 10 to the minus, I believe that's 10. Yeah. So you can solve for your Kb that way. If you know the Ka of the acid, you can find the Kb of the base. Realistically, you could also just look it up. But that is a way you could find that information if it wasn't given to you. So the Kb is 5.56 times 10 to the minus 10 equals X times X over 0.005 minus X, but I don't have to include that. I'm going to solve by multiplying 0.005, then take the square root, and I get X equals 1.67 times 10 to the 1, 2, 3, 4, 5, 6, to the negative 6th power. That gives you your concentration of OH minus. You can use that to find the POH. We're taking the negative log, 5.78, which means the pH is just 14 minus that, which is 8.22. Okay, that's a lot of stuff. The main idea here, though, is we are at the exact equivalence point, right? I've added the exact same amount of acid and base. If this were both strong, my pH would be 7, and I wouldn't have to do any of this work down here. But because this is weak, it makes some weak base, right? So I have to calculate the weak base's pH that you make, and it's slightly basic. So the pH at the equivalence point of this titration is going to be slightly basic. The strong base, you can think about it this way. The strong base with a weak acid, if they're exactly equal, the pH is not going to be 7, it's going to be just slightly above 7. And the opposite would be true as well. If you used a strong acid and a weak base, the pH at the equivalence point would be just a little bit below 7. All right, the last one looks like it's going to be really bad, but it's actually not too bad. So same reaction. I'm adding my, you might want to watch this video in parts, sorry. You're adding your acetate and OH minus reaction. We're going to start with that again. But we are almost done. This is the hard part. Or like this problem is the hard part for today. I'm going to add that to some OH minus. And you're going to make your products. Water. All right. So you're starting, again, another problem with your 0.005 of this. And we're going to start with none of our base. My OH minus, I'm adding a little bit extra. So I'm adding 0.1 molar 60 milliliters. I'm adding 0.006 moles. So I'm actually adding a little bit extra of the strong base. So all of my acid will go away and turn into conjugate base. I'll have none of this left over. I'll have a little bit of OH minus left over, and I'll make some acetate anion. What's nice about this, though, is you have a strong base and a weak base left over. Strong bases completely outweigh weak bases. Oops, I wrote this wrong, but it doesn't matter at all. This would be 0.005. But, right? Strong bases contribute significantly more OH minuses than weak bases do. So because of that, we don't have to do any of this work. we can find the pH just using this amount of OH minus. Okay. So what I'm going to have to do, I have 0.001 moles of OH minus. My new volume is, I have 50 milliliters of acid plus 60 milliliters of base. So I have 110 milliliters. So I have 0.00909 molar NaOH, or just OH minus actually. I'm going to find the pOH of that by taking the negative log. So I can find the pH of that by subtracting from 14. It's so much easier when you have a strong acid or base left over. You don't have to go through all of the other steps. All right, so to summarize what we're doing here, when you have weak and strong things, you're going to see what you're left with. You're going to react them with each other to completion and evaluate what is left. Every possible scenario is what we just did. We did, if you have weak acid left over, that means you'll also have some weak base. You have a buffer problem. If you're at the equivalence point, all of your acid and base you added will be neutralized and you'll only have weak base left. You have to do an ice table problem to find the pH. And if you add excess OH minus and you've completely neutralized all the HA and added a little bit more OH minus, you only have strong base left, so you can just find the pH using the pH formulas. So there are 4 different scenarios, basically, of what can happen, and that's an example of every single one. Okay, so to kind of summarize here, a strong base with a weak acid. Okay, in my head, I'm looking at this strong base. The base is stronger than the acid, so at the equal point, it needs to be a little bit above 7, which this graph shows. My equivalence point is right here, so right in the middle of this curve. My pH is like 8 point something. So okay, the pH at the equivalence point is always greater than 7. The other thing I noticed is this graph's not as smooth as the other one. This area over here is called the buffer zone. And you can see the transition in pH isn't nearly as smooth as it was before. It's a buffer zone because you are making a buffer in this range. You have some acid and its conjugate making a buffer, resisting that pH change. Now here is the opposite. This is the pH of a weak base and strong acid. To check which one it is, I do the same thing. I find the equivalence point, which is here, right in the middle of this curve transition. And the pH at the middle point is a little bit below 7. So the acid is kind of outweighing the base. Right? The graph isn't nearly as smooth because it has a weak acid or weak base in it, and you have this buffer zone up here where the pH is changing kind of not super predictably. It's not nice and symmetrical. Okay, so there's 2 ways to determine the approximate equivalent point of a reaction. The first one is kind of what we just showed you. You graph the titration curve. Use a pH probe and monitor the pH as you add the acid in, and that's essentially exactly what this graph was doing. You had a pH probe hooked up to your solution, and as you added in your acid, you could actually measure the pH. And this is a measurement of the pH over time, and you can use that to find the inflection point of this curve. That's the equivalence point. Okay? Or you can use an indicator, which is kind of what we will do in class more often. It's a little bit simpler, and it doesn't give you this whole nice curve, but it will let you find the equivalence point. So, the acid-base indicator at the beginning of the titration, when the color change occurs, it marks the endpoints of the reaction. And I use a slightly different piece of language here. The equivalence point is mathematically the exact point where the moles equal. The endpoint is just the end of the titration. It's always a little bit past the equivalence point because you can never perfectly add the right amounts. You're always going to have a little bit of excess of your titrants added because you're waiting for the color change to occur. And the color change doesn't occur till after you've added the amount of acid you need. So there's a technical slight difference, and I explained that here, I guess. The equivalence point of a titration, defined by the stoichiometry, is not the same as the endpoint, which is where the color change occurs, right? If you choose the proper indicator, it'll show that this error is not a big deal. You have to add 1 extra drop or something. So it's pretty much irrelevant. All right, indicators real quick are just things, or they're weak acids generally, that change color whether or not they have a proton. The general reaction, I don't think you'll ever see this, H indicator, so this is a proton with the rest of the indicator, whatever that is. It's a weak acid, so it'll lose a proton and make an indicator minus. The idea is that this chemical and this chemical are different colors. So when this reaction occurs, you'll be able to see the color change occurs. Okay. When we choose an indicator for our titration, we want to choose the indicator endpoint, where the color change to be as close as possible to the titration equivalence point. The dramatic change in pH near the equivalence point makes it easier to choose an indicator because the color change is always very sharp, usually occurring within an addition of a single drop. Okay, that one is a doozy. This is notoriously one of the hardest sections. We did a whole bunch of math practice there. We'll do a whole lot more as we go. Titrations and buffers are the most important part, probably for the AP exam, at least the math sections of it. So hopefully at least some of that made sense. Feel free to rewatch parts as you need. Really good examples for the types of things you need to know how to do for this section. Have a great rest of your day. Don't do any more chemistry stuff today. That's in order. Just try to take this in, and I will see you all soon. Have a good day.